So in this chapter we're going to take a look at minerals, and then we're going to dive into rocks. So we're going to see that both minerals and rocks is what's going to record the information for us that we're going to have to learn how to read in the rock record. So let's first take a look at minerals, because minerals are the smaller component of rocks. So in order to be a mineral, the definition of a mineral is actually pretty stringent. A mineral must first be naturally occurring, right, meaning it can't be made in a laboratory setting. It must be inorganic, so it cannot have, right, any organic carbon, right? So things like coal technically are not minerals. It has to be solid, which seems pretty obvious, but there are actually things that are very viscous or slow-moving liquids. For instance, glass is actually a slow-moving liquid. All glass, even the glass in your house. For example, if you've ever taken a look at old glass in an old house, you might notice that it's wavy. Or you might also notice that it's thicker at the bottom of the pane of the glass than the top. That's because it's actually flowing. It's flowing very, very slowly downwards, right? Being pulled by gravity. So our minerals cannot be glasses. They have a definite chemical composition, right? That's its fingerprint. Just like water has a composition of H2O, right? Every mineral is always going to have a chemical composition. Don't worry, I won't make you memorize those, right, for class. And they all have an orderly internal structure, right, which is also that's the chemistry part, right? That's part of their fingerprint. Minerals are the building blocks of rocks. When minerals get together, right, and have a party, that's when they form a rock, right? A rock can be composed of just one mineral, or it can be composed of hundreds of different types of minerals. We're going to see that each mineral is formed within a very narrow range. Okay? And we're going to use different physical properties to identify them. And as we learned, right, in Chapter 3, that some minerals have radioactive elements, which help us understand, right, when they formed. Now, as we move into this chapter, we're going to take a look at minerals first, and then we're going to talk about rocks. But remember, we're only going to talk about sedimentary rocks. So when you read this chapter, you don't necessarily have to read the information about igneous and metamorphic. You can if you want to, because they're pretty cool, but it's not necessary. So let's take a look at some of their identifying properties. One identifying property that stands out above the rest is color. Right? When you look at a mineral, that's the first thing you notice, right, is its color. However, color is not a reliable property. For example, down here, right, this green and pink mineral are actually the same mineral called feldspar, but it can be pink or green. It can actually even be white, okay? And that's because there's different chemical impurities in there that can give it different colors. So I can't always say, oh, every time I see a pink mineral, it's feldspar, because it could also be other colors, right? So colors can be used to kind of help us determine what elements are in there. For example, right, if I see a dark mineral, it usually means it has iron and magnesium in it. Or if I see a light colored mineral like these two here, that's telling me it has a lot of silica and oxygen in it. That's really all I can do for color. I can also take a look at luster. Luster is the way a mineral reflects light. Okay? And the way we look at luster is we break it down into two categories. We could have minerals that are either metallic or non-metallic. Of course, metallic means it's really shiny like a metal, right? It reflects light. And non-metallic means it's absorbing the light, right? It's letting the light through it, right? It's not reflecting it off. Another good identifier is taking a look at mineral hardness. And this is just the way, or this is the ability of the minerals to resist scratching. And the way that we determine this is by looking over here. This is Mohs scale of hardness. It goes from 1 to 10, with 1 being the softest and 10 being the hardest. So we've designated minerals, right, as you can see here, that have this. For example, talc, right, if you've ever used baby powder, that's talc. Talc has a hardness of 1, meaning it's very soft. Gypsum, the sheetrock in your house, has a hardness of 2, right? So it's soft, but it's not as soft as talc. If we move up the list, your teeth are actually made, and your bones are made up of this mineral, apatite, that has a hardness of 5, so it's a mid-grade hardness. Beach sand is mostly composed of little tiny grains of quartz. That's pretty hard, has a hardness of 7. And of course the hardest is diamond, right, which has a hardness of 10. So the way that we use Mohs scale of hardness is if I had an unknown mineral, what I would do is I would test it against these known minerals. So let's say a student brings me an unknown and I want to figure out the hardness. So I would take my mineral and then take number 1, talc. And I would see, can my unknown mineral scratch talc? If it can scratch talc, that means it's harder than a number 1. Let's say then I compare it to gypsum, and it can scratch gypsum, so that means it's harder than a number 2. But let's say I get to calcite, and it cannot scratch calcite. That means it's softer than a 3. So that means its hardness is right here, somewhere between a 2 and a 3. Right? Now, I know geologists are nerds, but most of us don't walk around with 10 minerals in our pocket all the time in case there's a hardness emergency. So we have things that we've designated hardness numbers to. For example, your fingernail has a hardness of about 2.5. Okay. A piece of glass has a hardness of about 6. Okay, or excuse me, about 7, right in here. Which is why you can test to see, right, if your fiance bought you a diamond, right? Diamond is harder than glass, right? So of course it'll scratch glass. So these are things that we would commonly have around. Another one that's very useful is taking a look at mineral cleavage. Now, cleavage is the way a mineral breaks. So, when we take a look at minerals, minerals come in 2 varieties. Either they have cleavage, meaning they break off in flat planes, or they don't, right, which means they just break irregularly. And the reason is due to the chemical structure. So let's say I have 2 minerals, right? Let's say here's the mineral's grains, there's number 1, and here's number 2, right? Here's the atomic structure. Let's say number 1 has a lot of chemical bonds, right? It's very strong. You see it's bonding all over the place. And let's say number 2 really only bonds very strong in this direction and then very weakly in this direction. So if I were to hit the first one, A, with a hammer, could you predict where it's going to break? The answer would be no, right? Because it has all of these strong bonds. So it's just going to kind of break irregularly somewhere across there. Now, if I hit B with a hammer, could you tell where it's going to break? The answer would be yes, right? It's going to break across these weak planes. So you see how it's going to break off into flat layers. Those flat layers is what we call cleavage. So, in order to understand cleavage, okay, and the directions of cleavage, I want you to envision a box. Let's see if I can draw this in here. I am not the best drawer on the planet. Okay, so let's envision a box here. 3-dimensional box. Alright, something like that. You get the idea. So in a 3-dimensional box, there's 3 different planes. You've got the top and the bottom. They sit in the same plane, right? And you've got this 2 sides. They sit in the same plane. And then you've got the front and the back, right? They sit in the same planes. So you have 3 different planes. Okay. So if we take a look, something that has cleavage in one direction is going to break off in one of these planes. So if you take a look here, you can see it's flat on the top and flat on the bottom. But it's broken, right, on all the other sides. That's one plane. Okay. Something that has 2 directions means it breaks off in 2 planes. So maybe it breaks off, right, if I were to take a look at it, maybe it's flat along the top and the bottom and the 2 sides, but then it's all broken, right, on the front and the back. And of course, then we can have 3 directions, right, which would be a perfect cube, right, if it breaks off in all 3 directions. It can have angles at 90 degrees, angles at more than 90 or less than 90, and you can see all the variations here within. Now the directions of cleavage actually goes all the way up to 12, but I think it's easiest to understand 3, so we're just going to take a stop there. Now, minerals that don't have cleavage have what we call fracture. That's where they just break. Something that has fracture, that mineral is telling us that it has a very strong chemical structure. It has very, very strong bonding in there. So, 2 great minerals that do that. Quartz, right? You've probably seen quartz before. Quartz has, amethyst is a type of quartz, that's the purple variety, has no flat planes in there at all, just kind of breaks irregularly. Now, some minerals, okay, this is actually a volcanic glass, so technically not a mineral, but it displays a pretty interesting feature. And all glasses do this. They break very irregularly because they have a very strong bond. However, I want you to notice, if you take a look at this volcanic glass, can you see these semicircles that are on here? Okay, we call this conchoidal fracture. That's a very specific type of fracture that's telling us we're taking a look at a glass. Now, some minerals are also magnetic, right, which means they probably have iron in there. A great example would be magnetite, right? If I put a paper clip on magnetite, it would attach itself. Some minerals, and we're going to talk about these type later on, react with acid, meaning if I drop hydrochloric acid on it, it's going to start to fizz like crazy. We're going to see that that tells us that we have minerals that are carbonates. So we're going to talk about that a little bit later on in this chapter and definitely the next chapter.